Okay, so welcome to this special afternoon on random matrix theory and combinatorics. One of the bonuses of the current situation is that we can have these sorts of meetings with people from all over the place. We can get speakers from anywhere. And also we can sort of join up with other groups. So this is something to be pleased about. So our first speaker this afternoon, I'm delighted to have that we've got Konstantin Tikhomirov, who's going to talk on singularity of random Bernoulli matrices.
Thank you very much for the invitation. I gave similar talks before, and this time I would like to try something a little bit different. I want to make an emphasis on some combinatorial component of the proof, but I have to sacrifice something, so I'll sacrifice a little bit of history. That's why I will be skipping some slides. Still, the problem I will formulate with all the details. So we have independent n independent random vectors, identically distributed. Each vector is uniform on vertices of the standard cube, -1, 1 to the n. So then the question is, what's probability the vectors are linearly independent? Equivalently, if we arrange these vectors into a matrix, represent them as columns of a square matrix, then the question is equivalent to the question, what is the probability that the matrix is singular or non-singular? So this is the global notation for this talk. I'm sorry. Global notation, this capital Bn will denote the matrix n by n with independent, identically distributed entries. Each entry is either +1 or -1, so symmetric sign variable. So this is some variational formula for the smallest singular value, which I'm going to use later. It's very important in this geometric approach to random matrices. Because the idea of the proof starting point of the proof is to decompose the unit sphere into some classes of vectors according to their properties, and then study the infimum over vectors from those classes separately, sort of utilizing some information about the vector structure. Okay, so this is the question I'm going to consider. I'm going to skip some motivation from numerical analysis. There is a motivation for studying the condition number of random matrices. So here I just want to mention that probably the first rigorous result on the distribution, the limiting distribution of the smallest singular value appropriately normalized, was obtained in the 80s by Alan Edelman. So here I just give a formula with the purpose of illustrating what should be the expected behavior of the smallest singular value. Here, capital Gn is the standard Gaussian matrix. The study of a Gaussian matrix is somewhat easier due to the rotational invariance and due to the fact that the joint distribution of singular values can be written explicitly. There is an explicit formula for that. So from this relation, it can be checked that the typical value, say the median, what is the median of S mean? It is of order 1 over square root n roughly. And the smallest singular value decays so linearly in the sense that this small ball probability here, probability that S mean is less than t over square root n, behaves roughly like t, because here when t is a small parameter, you see we can approximate this exponent by 1 minus t, and then this 1 cancels, so we have t plus little of 1. Well, in fact, we have t times 1 plus little of 1. But, this is the idea. This is what we should expect. In the discrete setting, the matching result was obtained much later. The first result of that type is due to Tao and Wu, and the paper is 2010. So a lot of techniques needed to be developed to get a result like that. But now I'm returning back to discussing the discrete Bernoulli matrix. In fact, the first non-trivial result on the singularity probability, estimating singularity probability of this matrix Bn, was obtained in the 60s by Komler. And he showed that when the size of the matrix goes to infinity, probability that the matrix is singular, so probability that the columns of the matrix are linearly dependent, goes to 0. And this little of 1 was bounded by maybe up to some log multiples by 1 over square root n. So a breakthrough result published in 95 due to Kahn, Komler, and Semeredi, they showed that probability of singularity is actually exponentially small in the dimension. And in that paper and the problem before that, already it was conjectured what should be the right probability here if we want to estimate probability precisely. So here are the two conjectures. The weak conjecture, which is solved, and the strong conjecture, which is still open. So how they obtained? So first, there was some intuition developed, and it was conjectured that the input to the event that the matrix is singular is mostly due to the equality up to a sign of 2 rows or 2 columns of the matrix. So about the lower bound for singularity, if we just consider this event, probability of this event, 2 rows or columns of Bn are equal up to a sign. It is not difficult to check that this probability is equal to 1 minus little of 1 n squared 2 to the 1 minus n. So how this result can be obtained? So the tricky part here is to check rigorously that the event that say two given rows are equal up to a sign is essentially disjoint from the event that 2 given columns are equal up to a sign. So so that we sort of can sum up the 2 probabilities for rows and columns separately when estimating the probability of the event. So anyway, this is the lower bound, which is conjectured to be optimal. So the strong conjecture is probability that Bn is singular is up to this multiple that converges to 1 with the dimension is n squared times 2 to the 1 minus n. And the weak conjecture is about the optimal quantity in the base of the exponent. So it is much more crude estimate. So the conjecture is that the singularity is 1/2 plus little of 1 to the n. So this is the this setting. Now, there have been a lot of progress on these questions and related questions when not only singularity probability, but actually the magnitude of the smallest singular value is of interest. And the model of randomness is much more general. So here, because I want to focus a little bit, if possible, on the combinatorial aspects of the proof, I will not discuss in detail, just give a very brief account of what was known before. So as I said, the breakthrough result of Kahn, Komler, Semeredi that established exponential exponential decay of the singularity probability. Tao and Wu improved the constant in the base of the exponent to 3 over 4. And Bourgain, Wu, and Wood later improved the constant to 1 over square root 2. So this is what was the best known result on the Singularity up to 2018. In fact, this paper contains some results which are optimal. It's just for the different model of randomness. So here I just give an example, but in fact, the techniques that they developed are more general. So an example is if you consider a matrix capital Mn, three-valued entries, +1, -1, and 0, and 0 with probability 1/2. Otherwise, +1 and -1, each with probability 1/4. In this case, it is elementary to see that probability that Mn is singular is at least probability that we have a row of zeros. But then if probability that the entry is equal to 0 is 1/2, probability that a given row is 0 is 2 to the -7. So you get a trivial lower bound. And then they showed that actually a matching upper bound is valid. Well, matching again in this weak sense when the base of the exponent is considered. So the techniques that they use are very different from what I'm going to consider later. So this is a very interesting approach, which was started by Kahn, Komlish, and Semeredi, and it's based on some replacement of the original distribution of the entries of the matrix with some other auxiliary distribution. Okay, so I'm going to skip some more discussion here and just mention this theorem of Rudolph and Vershinin, which was verified using geometric approach to random matrices. And this is much closer to the argument I'm going to discuss later. So this is what they showed. If you have capital AN random matrix with i.i.d entries, 0 mean, unit variance, and bounded sub-Gaussian moment, the later condition, this one with with a sub-Gaussian moment, it was later relaxed, so it's not that important. So they showed that in this case, as mean behaves in the same manner as in the Gaussian case. So this here just referring to this result of Edelman that I discussed in the first place. So there is certain sort of imperfection in the estimate, in the sense that this constant capital C is not sharply defined, and it is it depends on the sub-Gaussian moment. It's some constant which with not very good dependence on the sub-Gaussian moment. But the point is that when we take t equal to 0, we get that the singularity probability of the matrix is exponentially small in the dimension. This little c is strictly less than 1. Okay, so the argument is based on a few components, and I'm going to consider this one partition of the sphere into compressible and incompressible vectors, because it is important for the argument of the theorem that I'm going to discuss. Sorry. So here is some definition and some basic examples on what compressible and incompressible vectors mean. So we have a unit Euclidean sphere, Sn-1. We say that a vector on the sphere is delta rho compressible if Euclidean distance from this vector to the set of delta n sparse vectors is at most rho. So here I gave some example. We have a vector with 7 components on the sphere. So if we sort of chop off these small components, 3 components, we will get 4 sparse vector. And the distance from the original vector to this new 4 sparse vector is Euclidean distance, is square root of 0.03. So this vector is 4/7, square root 0.03 compressible. And the complement of the set of compressible vectors are called incompressible. Here I use terminology of Robertson and Verschi. So, so if I want to illustrate this, it would look something like this. So I have a sphere, then I pick, so here I have a sphere on R2. I have 4 one-sparse vectors, just plus minus coordinate vectors. And then I can say that these vectors in small neighborhood of the one-sparse vectors are compressible with appropriate choice of parameters. And the complement of the sphere are incompressible vectors. So when the dimension grows, it happens then if the parameters delta and rho are small, say small constant, say 1/100, and dimension grows, dimension of the sphere, the set of compressible vectors becomes small, small in various senses. So we can compute the surface normalized surface measure of the set of compressible vectors, and it will decay exponentially fast as the dimension grows, for example. But this metric is actually not interesting in this context. What is more important is that the size of the smallest epsilon net on the set of compressible vectors can be efficiently bounded from above. So here is the crucial lemma that I'm not going to use this very lemma, but something very closely related. So the idea is that if delta and rho are small parameters, we consider the set of compressible vectors on the n sphere. Then if we define calligraphic n as the smallest Euclidean epsilon net, okay, so this is the smallest set such that the distance from every compressible vector to the set Euclidean distance is at most epsilon. So if we define the smallest Euclidean epsilon net, then its size can be bounded from above by some quantity. This is not important, it's some technical details, but the point is this quantity is small in certain sense that it is a very efficient upper bound. And as a corollary of this lemma, a union bound probabilistic argument almost immediately together with certain classical concentration inequalities, it implies that this proposition. Here I also give it for illustration. Probability that if we have an, our matrix with i.i.d entries normalized, we can estimate probability that ANX, Euclidean norm of ANX, is small for some compressible vector X by something exponentially small in the dimension. Okay. So the idea of the proof of the proposition is just is a basic instance of epsilon net argument. So we use triangular inequality, and we rely on the fact that since the matrix has sub-Gaussian entries, its norm is of order square root n with probability exponentially close to 1. Okay, so this is some preliminary observations on the compressible set. So next proposition is about incompressible vectors. So I will not discuss this in detail, but it is some instance of first moment method. Very nice application of first moment method, which allowed actually in this paper of Robertson Verschi to get very strong quantitative bounds on this mean and not just the singularity probability. So here so this proposition deals with incompressible vectors. So the idea is to use the fact that if we have incompressible vector, I just recall what incompressible means. It is a vector on the unit sphere such that its distance to the set of delta and sparse vectors is greater than rho. And delta and rho are some small constants, like 1/100, say. And it can be checked that every incompressible vector has a nice property that a proportion of its coordinates are of order 1 over square root n. So the ideal instance of incompressible vectors, if it's possible to say that, is a vector where each component is 1 over square root n. So it is completely flat. Of course, not every incompressible vector is close to being completely flat, but still a proportion of coordinates will be of order 1 over square root n up to constant multiples. So this observation and first moment method allows to reduce the estimating probability of the infimum of ANX over incompressible vectors X to the probability that the distance between a given column and the linear span of other columns of the matrix is small. Okay, so ANX is small for some incompressible vector X only if the distance actually, I can say this in a more crude form, only if there exists an index I such that the distance between i's column and the span of other columns is small. But in fact, something more precise holds. So here we have some weighted combination of probabilities. Okay, so please let me know if I need to stop and clarify some things, because I have been going fast through some of the slides. Okay, so here is the summary which I'm going to use in the proof. So we start by estimating probability that S mean of the matrix AN is less than or equal to T over square root n. So T is some parameter. So how we estimate this probability? First, use variational formula for S mean. So then the probability is upper bounded by the sum of the two probabilities when we take the infimum over compressible vectors and incompressible vectors. And then the compressible part is estimated by something exponentially small due to the fact that the metric entropy of the set of compressible vectors is small. So we can construct small epsilon net on the set within the set of the compressible vectors. And the second is estimated using this first moment method approach by probability that the distance from nth column to this linear span of the first n minus 1 columns of the matrix is at most T over O. And here the summation, you see the summation of probabilities that was in the proposition on the previous slide. It disappeared just because in our model the distribution of the matrix is invariant under permutation of columns. So for every I, the distance from i's column to the span of other, except for the i's, is distributed the same. So we just pick some index. I will work with the last column and the linear span of the first n minus 1. Okay, so here is the idea, and now the question is how to estimate this probability. And this is, of course, the main sort of, this was preparatory work in the Ruderson-Vershinin approach. It was a preparatory work, and the essence of the argument is estimate actually how to bound this probability. This is the technically most difficult part. Probability that the absolute value of the scalar product of nth column and the normal vector to the first n minus 1 columns, the unit normal, is at most T over O. Okay, so let me now go to the statement and the proof of the theorem. So here is the statement of the theorem. It has the quantitative part. And the as a corollary, the resolution of the weak conjecture. So the quantitative part is that for every epsilon, there exists a constant, capital C, depending on epsilon, but it is not allowed to depend on T or N, only on epsilon. Such that probability that the smallest singular value of our Bernoulli matrix, Bn, is at most T over square root n, is bounded from above by, so this is the linear term here, similar to what was observed for the Gaussian matrix as the earliest result in that direction. And this atom sort of the distribution, which has the right quantity in the base of the exponent, because we can take epsilon arbitrarily small, and then we get probability of singularity 1/2 plus little of 1 to the n, and get the weak conjecture. Okay, so here is some. I wanted to mention here some results, more recent results, or just a few years old, maybe, dealing with singularity of random matrices. So a lot of results. Actually, just about a week ago, there was a paper posted on arXiv about singularity of random symmetric matrices. So it was shown that the singularity of probability of random symmetric Bernoulli matrix is exponentially small in the dimension, and it's of course it is a breakthrough result. So just wanted to illustrate how active this this area is. A lot of new results. So okay, so returning to the theorem, let me now go with the proof. So I want to get to the combinatorial part of the argument. So I will discuss with not much detail the preparatory work. So here the lemma stated here matches lemma of that I had on one of the previous slides. It is from the paper of Litvak, Pajor, Ruderson, and Tomczyk-Jagerman. So it was a paper on random rectangular matrices, but it was probably the first paper where this idea with the small metric entropy of the set of compressible vectors was used. So here what we have, we fix parameter epsilon, and then we just say that there is delta and rho depending on epsilon and n0 depending on epsilon, such that for all n bigger than n0, probability that bnx is small for some compressible vector x is at most 1/2 plus epsilon to the n. Okay, so before that, what is the difference with the previous statement? Previous was with upper bound 2 times exponent minus Cn, and the constant C was not specified. But in our setting, we really need to specify the constant. We need we are working to get the right constant. So this is a modification of the argument that is absolutely necessary. But it's very simple. It just follows the lines of the those old observations. So now we have probability that S mean is less than T over square root n is 1/2 plus epsilon to the n. This is a good term. And now we have this probability that the scalar product of nth column and the span and the normal vector to the first to the linear span of the first n minus 1 columns of Bn is at most Ct. C is some constant. Okay, so our goal here is to estimate this guy is when T is equal to 0, at least by 1/2 plus epsilon to 0. So goal. So when t equals 0. Of course, the quantitative estimates require something more, but here I'm just discussing the singularity conjecture. For the singularity conjecture to be confirmed, we need to check that this probability when t is equal to 0 is at most, say, 1/2 plus epsilon to the n. Is at most, say, c tilde 1/2 plus epsilon to the n. And once we show this, the conjecture will be verified. Okay, so this is the goal. Okay. What is the idea here? So this is a technical part of the talk. The idea is to show that the vector, the normal vector yn, is typically very unstructured. So in what sense? So the idea is to show that the scalar product of yn with nth column behaves like a variable with bounded, as a smooth variable with bounded density function. Of course, this is not the case. This is a discrete random variable. But the idea is sort of you can see the discrete nature of this variable only if you zoom in really up to the scale 1/2 plus epsilon to the n. So how to make this more rigorous? So here is some auxiliary set, capital Qn. It is the set of incompressible vectors satisfying certain condition on the Levy concentration function. So here I recall what the Levy concentration function is. So this is the definition. If we have random variable xi and we have parameter t, we define the Levy concentration function of xi with parameter t as the supremum over these probabilities. What these probabilities means? It's just the measure of the interval of length 2t. So imagine that we have we consider all intervals on the real line of length 2t, and we take the supremum over their measures. The measure is the one induced by the distribution of xi. The measure induced on R by the distribution of xi. So now apply this definition to what variable we want. Xi in our case is the scalar product of the nth column of Bn and our vector x. The vector x is non-random in this definition. So we fix some unit vector x. So now the idea is to define the set of incompressible vectors such that the Levy concentration function is so if we consider the supremum of all t such that the Levy function is bigger than capital LT, will be roughly of order 1 over capital N. So capital N here is a parameter. 2 minus epsilon to the n is the upper bound for this parameter. Capital L is a constant. But now, what this condition actually means? So how this condition can be interpreted? So first, imagine that the variable, the product of nth column and x, is a smooth variable with uniformly bounded density of the distribution. So of course it's not the case, but let's imagine that this is the case. So what we expect from the Levy concentration function in that case? Well, if the density is uniformly bounded, say by a parameter capital M, then the Levy function at point t can be at most 2m, at most 2m, 2m times t, I'm sorry. So for every value of the parameter t, the Levy function would be at most 2m times t. But here the variable is discrete, so this rule does not hold for small t. We should expect, if we want to graph the function, so this is the Levy function, and this is the value of the parameter t. And this is the Levy function of this variable nth column with x at point t. So if we want to graph this function, what we expect to have? So we expect to have the following behavior. So it is roughly linear decay up to certain threshold. And after that, it stops being linear because we find some atom of the distribution. So it is maybe constant, or at least it stops its linear decay. So this threshold where this transition from almost linear to essentially non-linear decay happens should be roughly at 0.1 over n. Okay, so this is what the condition on Qn means. So this is you see, if the transition happens at point 1/2 plus epsilon to the n, then it would be great for us, because then we take t equal to 0 and we immediately get an upper bound, the needed upper bound for the probability that the scalar product of nth column and x is 0, and so this we would be done if x is the unit normal vector. But here we don't know that, so we need to partition the set of incompressible vectors according to this threshold for now. So we partition into this set Qm, and now the goal is to say that probability that our random normal, the normal vector to the first n minus 1 columns, belongs to this set Q capital N is at most 1/2 plus epsilon to the n for every choice of the parameter capital N, at most 2 minus epsilon to the n. So the vector yn is required to be unstructured exactly in this case. So if we take the scalar product of yn and the nth column, then this variable it shows linear decay of the Levy function up to the threshold 1/2 plus epsilon to the n. Okay. So the next stage of the argument is the discretization stage. So okay, so we defined our set Qn, and we want to show that probability that yn belongs to Qn is very small. So what can we do? The idea is to use epsilon net argument, but the construction of the net here is more involved than in the case of compressible vectors that I discussed before. So the first step of the construction is to observe that we can find an approximation. So given any realization of yn and qn, we can find its approximation. So this I denote by boldface y in the rescaled integer lattice. So here is the scaling parameter, 1 over capital N square root dimension. So this vector satisfies simultaneously several conditions, this approximation. So first, it's a good approximation in L infinity norm. But if this was the only condition we wanted, then it would be, it would be a triviality, of course. So we need some more assumptions on this boldface y vector. So, and there are some assumptions that we can guarantee. So first, some anti-concentration condition, which means that probability that the linear combination of yi, where here bi's are i.i.d plus minus 1, so i.i.d symmetric sign variables. So probability that this linear combination is at most c is bounded from above by CLT. So C and L are both some large constants. And this holds for all t bigger than threshold 1 over capital N. Another condition is the sort of the opposite condition, concentration. The Levy concentration function of the linear combination with the components of this approximating vector boldface y is bounded from below by the Levy function for the original vector yn. And the last condition that we need is that the matrix vector product, so here B is here by B1 and minus 1 transposed, I denote the matrix that is obtained as follows. So we have our square matrix Bn. So these are, just recall, these are the first n minus 1 columns that I'm considering. Yn is the vector which is orthogonal to this first n minus 1 column. So what we do, we first we transpose this matrix Bn. So we take Bn transposed. So we now have these first n minus 1 columns become first n minus 1 rows of the transposed matrix, and then we just remove this last row. And this is how we get this matrix B1 n minus 1 transposed. So the condition is that this matrix times the vector y in the Euclidean norm is at most c square root n over capital N. You see, when we take yn, then this quantity would be just 0 by the definition, because yn was defined as the normal to the linear span. But here we just have some upper bound. This matrix vector product must be small. So this construction uses randomized rounding. It's a very well-known technique in computer science literature. So this vector boldface y, it is constructed by the random procedure. So you start with the vector yn, and then you sort of replace each component of yn with one of two values. So we consider two adjacent values on the rescaled lattice, either truncation below or truncation above. And then we reweight the probabilities in such a way that expectation is exactly the value of the corresponding component of yn. So this is a random construction. Once we condition on realization yn, we have some randomness to construct vector boldface y, and then we just show that with positive probability this random vector satisfies all four conditions. So we can just pick any realization satisfying all these four conditions. Okay, and here is some last slide before the combinatorial statement. So what we have now, we want to show again that a probability that yn belongs to this bad set, capital Qn, is very small. So we constructed approximations for every realization of yn. We can construct its approximation y from the rescaled lattice. Now denote by this calligraphic n the set of all realizations for all realizations of the approximation boldface y for all possible realizations of vector yn and qn. Okay, so what is important here is that this is a subset of incompressible vectors in the rescaled lattice satisfying certain conditions. First, the Euclidean norm, say between 1/2 and 2. And second, some anti-concentration and concentration conditions for the linear combinations, bi, yi, where bi are i.i.d sign variables. So, okay, what it gives. So now we apply epsilon net argument. So probability that yn is in capital Qn, it can be checked that it is contained in the event by epsilon net argument. It is contained in this event. Probability that we need to estimate probability that the matrix vector product is small for some vector in the set of approximations in this discretization set. So then we can upper bound probability in question by this number. So from now on, all probability associated to the matrix, to the Bernoulli matrix, disappears completely. We don't have anything left. We just have some statement that requires certain counting. So we want to show that this quantity is, so goal, to show that this quantity is at most 1/2 plus epsilon to the n. The problem here is that this C tilde, the constant that appears in this estimate, is really cannot be well controlled. It is a constant, and it is a very big constant. So because of that, we want to show that the set of approximations is at most n over, so here I use the notation c hat, n over c hat to the dimension for a large enough constant c hat. So here we don't have access to control c hat efficiently. It is a very large constant, and the trivial upper bound that we can get, for example, by considering by using only the property that this set of approximations is in the rescaled lattice, and this set has the Euclidean norm at most 2, so we can trivially upper bound the size of this set by the size of the intersection of the lattice with 2b to n. So this upper bound is absolutely not sufficient. So here is the combinatorial reduction, so now no Bernoulli matrix is left at all. So this is what needs to be proved, and once the theorem is verified, it implies the main result, and it implies this weak conjecture. So the theorem is actually not exactly what needs to be proved, but here I simplified a few things. So let's first consider this set. So this is a set on the integer lattice. So here I rescaled everything for convenience. So this is a Cartesian product. Here we just have integer interval from minus capital N to capital N. Here we have union of two integer intervals. So we have interval from minus 2n to minus n minus 1, and we have interval from n plus 1 to 2n. The reason why we need the union of two intervals rather than a single interval is that we want to separate certain components of our vector from 0. This is the idea. So we separate these delta n components of our vector from 0, and the rest we don't care. So okay, so we have this restriction on the parameter capital N at most 2 minus epsilon to the n. We have this Cartesian product, this set capital A, and now we have a random vector uniform on the set capital A. So this vector xi1, xin uniform on capital A. So you see, because A is a Cartesian product, this random vector has mutually independent components. Also, no identically distributed because so the first delta n components have different distribution from the last n minus delta n. So okay, we have mutual independence. And now what we want to show is the following relation. So what this thing actually means. So let's see. So here I have an indicator function of the interval from minus square root dimension to square root dimension. So, and the argument here is lambda plus linear combination of my random vector xi with the vector v. And the vector v is just a vector, is just a vertex of the discrete cube. So I consider the sum of these indicators, over all vertices of the discrete cube. So here is the normalization factor. Because I have 2 to the n vertices, I normalize by multiplying 2 to the minus n. I take the supremum over lambda. And I want to show that probability that this quantity is bigger than some large constant over capital N is super exponentially small in the dimension. So why it is super exponentially small? The crucial thing here is that I can pick m as large as I want at expense of increasing the threshold for n for the dimension, the lower bound for the dimension, but the parameter LB stays the same. So it's very important that these two parameters are sort of decoupled. LB can be a large constant, but still I can take capital M much larger than LB, and there is no interdependence here involved. So what is written here is actually just the explicit way of writing the Levy concentration function with respect to the randomness of the vertex V of the cube. Sort of what happened here is sort of inversion of randomness, because before that we were considering vertices of the unit cube as random, but now we sort of consider them as non-random, and instead the randomness comes from the distribution on this auxiliary set, okay, graphic A. So how this theorem can be in principle translated to the estimate of the cardinality of the net that I was discussing on the previous slide. So the idea is that we sort of test whether a given point belongs to the net. And it can be checked that a point on the rescaled lattice, if it belongs to the net, capital N, calligraphic N on the previous slide, then this point up to appropriate rescaling must satisfy this condition. So if I pick some realization of the vector psi, and I know that it's rescaling, I need to multiply it by 1 over capital N square root dimension. If it belongs to the epsilon net, then this condition must be satisfied. But now, if I know that probability that this condition is satisfied is at most e to the minus capital Mn, then I immediately get upper bound on the cardinality of the net. So this was the quantity from above. I will get an upper bound e to the minus Mn times cardinality of 1 over n square root n z n intersected with twice b2n. And because m can be taken arbitrarily large, I can make this quantity much smaller than any multiple of, let me roll back for a second. So what I need capital N over c to the n. So I can easily get any constant c hat that I want. So arbitrarily large. And once this is verified, all glues together and we get the main statement. Okay, so the idea is to study this this probability, and it is done by considering certain sequence of averaging functions, and then sort of tracking evolution. We start with certain function. So here the function will be would be an indicator of the interval minus square root n square root n, and then we consider certain random averaging operators, and we check how the L infinity norm of certain of these averages develops using some counting arguments. Okay, so that's probably everything I have time to discuss. Thank you very much again for the invitation.
Great, thank you very much. So if anyone would like to ask questions, please feel free to unmute and ask, or ask in the chat.
I do have a question.
Please go ahead.
Yeah, so I'm wondering about the so the bound you get in the theorem is about, you have the bound that the Sn times square root n is less than t. And then, of course, what you show here is what's happening when t equals 0, the probability of a singularity. But the behavior, I mean, the limiting distribution of Sn times square root n is known, right? It's supposed to be this is, at least in the Gaussian case, this was done by Edelman, and then it was generalized to
absolutely yes.
So and then of course you would expect that this constant time t. Now let's look at the other limit. When t becomes larger, the constant time t should saturate like an exponential. It should be 1 minus exponential minus t or something like that, right? The CT, because the limiting distribution is like an exponential. So is that done? And would you have the corresponding lower bound, including the one with the singularity? I mean, because you could ask yourself, what is the probability that this thing is smaller than square root n t over square root n and look at the lower bound, which might be like this.
Okay, so I think that everything that is known works in the range polynomial in n. So what is known is that, yes, as you said, so S mean of Bn, if you compare the distribution of S mean of Bn and S mean of Gn, so I need to normalize, I need to multiply by square root n. So the Kolmogorov distance would be up to appropriate coupling would be n to the minus c. So if the so you can bound from probability that this quantity is less than t. You can bound it both from above and from below by the corresponding probability for Gn, but the error additive term that you will get will be n to the minus c.
Yeah, so this exponential thing that you get will not give it, I see.
Yes, so for sort of two extreme values of the parameter, it will not give non-trivial estimate. Yes.
So then, if you allow me, there have another question in the same direction. So this is of course talking about the hard edge of Pastor-Marchenko matrices, right? And it's known since Forrester after Edelman that you have asymptotics in the same scale, which are now where the limit now is a little different from the exponential, is a bunch of Bessel kernels. But so for instance, here the question would be, what is the probability that if you take now n vectors in dimension n plus 18, that they are independent? Right, because this would correspond to a Pastor-Marchenko matrix where you have n times n plus k, where k is fixed. And there, it's known that the singular value, the small singular value, also fluctuates in the same scale, and the limit low is whatever it is, a little more complicated than exponential, but it exists. So it's in the same time of order of magnitude. So the question about this probability of the singularity would translate to what I just asked. Right? What is
okay,
so n vectors in n plus 18 dimension that they are here you're looking at n vectors in dimension n, but what about n in dimension n plus 18?
Let me think.
You know, that's why I was asking.
So,
the Gaussian
okay.
case is known. If you take the Gaussian case, this is understood by Forrester, and then it has become proved to be universal by initially by Sandrine Péchet and myself in a simple case, and then Yao and probably Tao and Wu. So, but here it's a nice combinatorial question. What about n vectors dimension n plus 18?
Yes. Let me think. So, so if you ask him what is the probability that the rank of this matrix n by n plus 18 matrix is n minus 1, so yeah, I think it can be checked that it is 1/2 plus little o to the n, and because in this case you see you will still have the singularity, this rank deficiency coming from, say, if you arrange your matrix such that it has say n rows and n plus 18 columns, then the rank deficiency would come from equality of 2 rows up to a side. So from the columns, the chance will be very small, but from the 2 rows, you will still get this 1/2 plus little o to the n.
Thank you. Thank you.
So this might be a good moment to pause, and we can have further questions during the break. So I'll stop the recording at this point.